that's where you come up with it. And also, like, you have to think about this is like how many samples you show pre-qual.
Yeah.
And when you do, 100, then you have 100 reference. But none of this is the same thing.
Oh, but you should have a single support for
Eventually. Okay. So that's what this is. That's what this is. We can say canvas versus showing one given.
So you have 100 images? You have 100
No, 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 no. I have the I have 14 and 16.
Yeah.
It's just like another tabs.
Your personal
When I do the
Yeah. But the lab's like, see, so for our program, you can like 12 of your units can be undergrad. And I was able to transfer like 8
So
from
N
UNA,
was
so
what
that was kind of nice.
Yeah. So N was cool. So
Yeah, I really want to do this now because it's like really cool.
but
This person is
This time it's done as PIE student chapter for optics. Yeah, Dr. Yeah, the Dr. Yeah, you went to our lab.
Making sure that you have the information along.
Yes, yeah, I remember.
it's like 30 bucks a year.
It's more.
Is it? Oh, I was experimenting for a while. It was like a student fee wasn't bad. It was like 30 bucks or something. But we were
It's
talking.
comparable to OSA students.
Okay.
It's gone
Thank you.
OSA students at $90.
Are there? I don't remember when I did that much.
Okay. We don't need to include that.
You don't have to include all the.
Well, oh, there's a student chapter of OSA here too. It's not very active, but
Yeah.
it's just like it's not like
What tea did you use for the second one? Because like I couldn't get my lines to be like as concise.
He was.
I think I used 512s.
They were. Oh, it's not. That's weird. I screwed up the wrong one. They were 0.
Oh, for this tea?
For the second team. You're asking about the one that was like the second one that was original, right? Like this one?
Yeah, yeah.
And you're asking what this team was for?
No, the just with the coefficients like A, B, C, D.
I got 1/2 cosine and -1 minus 1 cosine.
Oh, you didn't have the double cosine here, remember?
No. Because you just need the symmetry about the -2 and the -1. It's fully defined.
So that's just so it over defines it when you have that other one in there.
Yeah, you don't need it. So you have the least number possible. And also you want it to be 0 here.
Exactly.
So before
I couldn't get that to happen right there.
Right. Yeah. So that's why you do the negative.
Yeah.
1/2 for the second one.
Right.
That's what gets rid of the cosine.
Exactly.
Because that's 1.
And then let's see. So these are your results for Burlington. Oh, that's really nice. Mine like a little more rippled.
Yeah, I'm not sure. That's something we can't.
Because mine had like a little
Huh?
Apologies for being late. The Corey elevator literally kept me waiting 8 minutes.
I have a question.
Yeah, sure.
With the final project, is that just going to be a paper, or is there a presentation component to it? Or?
It's in the handout. The one in the handout, there's an announcement somewhere. I'm going over the many details of it. Just passing on. It'll come to me. Anything. Okay. Let me. Did everybody get a copy of the handout? Are there any extras left over? Okay. So let me just quickly go over the salient points of the handout. I won't explain everything because otherwise it would take too long. And what's the point of the handout if I go over everything already? So let's see. You have two choices. You can either do a term paper on a topic of your choice, and I'll explain what are the things that I expect in a term paper, or you can do a project. In either case, the term paper, it's the topic of what you work on needs to be mutually agreed. It can come from you. There's a bunch of suggestions here, and kind of the process that we go through is you submit a one-page proposal, not this Friday but next Friday. I'll take a look at it, and then the following Wednesday, if I feel that the project or the paper or the topic you're proposing is too far off from the main topics of the course, or it's too ambitious, or it's not ambitious enough, or it's too vague, I'll give you feedback. So we'll kind of try to converge on this project choice by the end of the by mid-March, or maybe March 24th or so, before the spring break begins, because March 24th is the Friday before the spring break. And if you end up, so what I've done here is I've suggested a number of projects and also a number of paper type topics. Many times there's for example, section 1, it's paper or project. So I'm suggesting something, and you can either do a literature review on it, or you can actually do a real project. There's going to be a presentation on the last Friday of the class, which is Friday, May 5th, if I'm not mistaken. Is the last day of instruction May 12th or May 5th? I think it's probably May 5th. I'm almost sure of it. If it is not, we'll just make it the last day of the class. And depending upon how many groups you've divided yourself, the presentations might take just one day or might take 2 days that week. I also reserve the right to possibly have the presentations occur during the scheduled final time for the class. We'll just meet here and everybody gives a presentation. don't buy your plane tickets yet, or don't bank on the time of the presentations yet. As we get closer, depending upon how fast and how much of the material I need to cover we've covered, we might use the last lecture of the semester, or we might just end up using the scheduled time, final time. I've done it both ways in the past. So if you end up doing a project, it's very important. Many of you are doing projects that you've already done something on, and it's an existing project that you want to enhance with something related to image processing. It's very important to, in your proposal, to let me know exactly what you've done in the past, where you are now, and exactly what you hope to accomplish as part of this course, so that it's clear that you're not going to just recycle something you did for your master's thesis 3 years ago as a term project for this. So we need to have a little bit of a checks and balances. At the same time, I don't want this project to get out of hand. Roughly speaking, let's see how many weeks by the time you start working on this, which is, let's say, next Monday, we have approximately 7 or 8 weeks to the end of the semester, right? And I don't want you to spend more than 5 to 10 hours per week on it. So the total amount of time you invest in this should be no more than 5 times 7 is 35, or upper bounded by 70, somewhere in that range. It's supposed to take roughly the same amount of time it took you to do the homeworks, because and there's probably one or two other lab assignments. So subtract some time off of that. So don't think of it as a humongous thing that you have to do. The other thing to notice is that I would strongly encourage you, regardless of whether you do a paper or a project, even if you do a paper, to team up with each other. Because many of the topics I'm proposing are very broad and have a lot of components. So what might make sense is to say, okay, you make a team of 3 to 5 people, and one person investigates this branch, the other person investigates this branch, and even if you want to compare the results, if it then turns out being a project, then it's much easier to have more people on your side. But at the same time, you have the flexibility of doing a single investigator type project. I'm not going to frown upon it. But I would encourage that you team up with your classmates. Initially, I put 3 topics down on paper last night, and then when I woke up this morning, I said, gee, what if they really don't like those topics? So I added 2 more. For a class of size 20, I think 5 topics is enough. However, if you don't like any of these, and you don't have any idea what other topic you want to work on, come talk to me. I can just kind of interview you a little bit, find out what your interests are, and then I can suggest something else. Okay? So don't despair if what you read here is just way over your head. You have no idea the terms mean, how it works, etc. Come talk to me either after class or in office hours. I'd love to talk to you about this stuff. Now, so for projects, it's very important, as I said, to delineate what you've done already and what the increment that you plan to do next is. For papers, let's say you pick a topic that you want to work on. The kinds of things that you want to do, I've written it here, but basically you want to do a literature search. You want to know what the state of the art is in this field for this problem. What are the techniques people use? You want to provide a bit of a critique. I mean, one of the things you'll do, maybe not so much as a graduate student, but once you get your PhD and leave Berkeley, is scientists are always evaluating each other's work. I mean, God knows how many trips we make to Washington, D.C. on these NSF panels to read umpteenth proposal, rank them up, critique them. This was good, this was bad, I would solve this problem this way, there's a flaw with this approach. So or you review other people's papers, even if you're not reviewing proposals. When you submit a paper, others review it for you. When you sit in your office, you get bombarded by papers to review for others. So besides just reading the literature, once you read enough of a paper in an area, you should be able to judge the quality of papers. First of all, you do that by seeing how well the paper is written, but also in the context of that field, at the time that paper appeared, did it really offer a significant novel increment to the field? Was it just a regurgitation of what was there already, or was there a delta step up? And sometimes these things get lost because the papers kind of get piled up. You look at 20 papers, you forget to read the dates and forget to read the precedence of the papers. So generally, the researchers who come up with an idea first and kind of lead the research community in that direction from that moment on, those are the ones that get the most credit. And those are the papers that should get kind of rated the highest. What was there before that paper, and what new thing did that paper suggest that made hordes of people follow that and continue that line of work, kind of breakthrough ideas. After 20 years after a paper is published, the significance of that original paper kind of goes down. People tend to forget about it. The students only read the most recent paper. They forget who proposed it first. But it's very important to kind of critique papers in terms of what was there before and what the paper introduced. And then the third component I want to make sure is in your papers is it's kind of a thought process or a hypothetical process. Is imagine yourself wanting to do a thesis in that topic, and I'm hoping that that topic is interesting enough that you can, for a few minutes or few weeks, you can imagine that. What would you do? What are the approaches you would pursue? What are the techniques you would pursue? Of all the techniques proposed to solve that problem, which ones do you think are most promising? Where would you put your energy, resources, and time if you were going to spend the next, I don't know, 3 to 5 years doing a PhD thesis on this? Okay. So I hope you have a kind of a clear idea. Besides the proposal, the term paper is due. I said that somewhere here. Did I put this down? Forgot to do it at the end. Yeah, do I say that? I can't find it myself. Oh, okay, good. I should have put all the deadlines in one paragraph. Okay, good. I did pick May 15th. So Monday, May 15th at Rosita's office at 9 a.m. And the people who tend to do just a literature review, a report that's no more than 20 pages double spaced, and people who do the project report that's no more than 10 pages double spaced. It doesn't mean you have to hit 10 and 20. It has to be upper bounded by that. So a 5-page report or a 10-page report is just as acceptable as 10 and 20. Again, I don't want you to make a monstrous big thing out of this thing. Something that you feel that exposed you to a part of image processing and made you learn something. So that's all I have to say about logistics. Are there any questions or comments? Okay, so I will very briefly go over each of the topics that I mentioned. Some of them, some of the things I put down on this paper is really verbatim out of some of the proposals I've recently written and got funded. So, or not funded, I can't remember. It's a mixture of everything. So some of them come across more like as a proposal, and there's many subtopics within there. We propose to do this, we propose to do that. So don't get thrown off by that language. You can pick any one of those areas and dig into it deeper, or you can pick a collection of the subtopics and dig into those. So don't despair. So topic number 1 is kind of in the intersection of multimedia and networking. There's a new thing called overlay networks that people have come up with in the networking community that facilitate many functionalities that are not easy to implement on the internet. Basically, internet was designed with quality of service not in mind, which is why we have such a hard time sending audios and videos and other real-time communication stuff on it. So I first list a bunch of approaches that people have applied on the traditional internet, and now I'm asking you, given that overlay networks are gaining more popularity, what are some ways that we can use these techniques to come up with ways of taking advantage of overlay networks to facilitate multimedia communication? So if you don't have a very strong networking background, haven't taken 122 or haven't taken possibly CS268, this would probably be a hard topic for you to tackle. Paper number 2 is also kind of an intersection of multimedia and networking. It has to do with wireless LANs and video or multimedia communication or video transmission over those. And so there's a lot of recent buzz about cross-layer design, where you let, what do I mean by cross-layer? Where you can think of communication over networks as having a bunch of layers, all the way from physical to link to transport to, sorry, the IP layer, which is the routing, then the transport, and then the application layer. And so people are suggesting ways, and these abstractions are made so that to make the design of the systems easy, so that you can also plug and play different systems against each other. And people have come up with ways of linking these different layers in order to facilitate wireless multimedia communication. And I've put down 1, 2, 3, 4, 5, 6, 7 papers. A lot of them, 6 of them is by this fellow Lendik, whose name I can never pronounce. Even though I just wrote a recommendation letter for him, I still can't pronounce his name. It's a Dutch name, but nevertheless, Eennlb is his first name. Reginald is his first name. So 6 of them are by him, and the 7th one is by Magda Elzaki, who's also quite famous in the field and is at UC Irvine. If you haven't taken this simple course like 122, this would probably be a hard topic, but very worthwhile to investigate or to write about. Number 3, 3 and 4 is what I added this morning when I just woke up. I said, look, these guys might not have too much choices. So number 3 could be a paper or a project. It's content-based search and retrieval for video and images. So as I'm sure you know, by playing with search engines like Google, Yahoo, and Amazon and MSN, there's and with the advent of, well, I don't know, MP3 songs and videos on handhelds, videos on your VCast cell phone, videos on your cellular cell phone, which Cellular just announced yesterday they launched video services. There's lots of multimedia data sitting around in the world. And the question is, how do you do, the same way as we do Google searches on text, how do you do search and retrieval on multimedia data? And the latest issue of IEEE Signal Processing Magazine, which I just got in my office yesterday, is the whole thing is devoted to this. So you can't even ask for anything better. Because the reason is you want to look at the latest because they all refer to the older articles. It's a fantastic topic for you to do a literature survey or a paper on. Now, if you want to do a project on that, most recently NIST announced a competition whereby they provide, it's a fairly structured competition with lots of boundaries and definitions and stuff like that. So they're providing people with a bunch of data, and I forgot how many hours of video it is. And they've already segmented it into shots. For those of you who are not familiar, the shot has a specific definition and meaning in video. It's if I have a camera and if I'm taking a picture of a person, a shot is a set of contiguous frames that correspond to the same locale. If I just then move to a different part of the room, and that's a different shot. So the shot segmentation of these videos have been done, and they have a bunch of competitions. I think 3 or 4 different categories of competitions, like kind of like Olympics, where one of them is they provide a set of keywords. The mic is off. It says on. Oh, power off. Off? No, on. Is it on now? I didn't change anything. Is it working? Okay. Well, that might provide a lot of motivation for people to attend. But we don't want to penalize them. Actually, they can't hear us, so we can say anything we want about them. No, just joking. Mute on, power off, power on. So I didn't change anything.
Can you just stay close to the desk then?
Oh, this is the mic as well? Okay, I'll try not to move too much. Okay. So, yeah, so they released a ton of video. I forget, I think 100 hours, but the video that's been pre-processed, so it's divided already into shots. And what you can do is, and then they've also released a bunch of keywords. I forgot 40 keywords. And these videos also have audio associated with them. Some of them are actually in English, some in Arabic, some are in Chinese. Don't ask me how they pick those languages. And the competition is on, you supply the keywords. The one that I'm interested, or I find most interesting, let's put it this way, there's 3 others, is you supply a keyword and you're supposed to retrieve pieces of multimedia, video and audio, that are synced together that refer to that keyword. The keywords are things like, I don't know, fire, terrorism. I can't remember all the details. Some of them you definitely have to use the speech recognizer and the transcript of the clip in order to recognize this. For example, democracy. Look, how can you look at the video and say, oh, that's about democracy? You can't. It's the words and the audio that's important in classifying that as a democracy piece, right? And then there's some other ones that are more action oriented, like, I don't know, fire. Like, that's very visual. You see flames all over the place. So, and I'm just drawing blanks with all the other keywords, but there's 40 of them. And so if you want to do a project, you can download these things, and I'd be happy to help you. I didn't put a lot of detail in this, mainly because I did this in the morning, but if there's interest from any of you, I can put you in touch with the right people to get access to the data to do some interesting stuff about it. Topic number 4. So it has to do. It's a fairly mathematical topic for those of you who are interested in more theoretical stuff. It has to do with signal expansions along over complete set of basis functions and applications to video coding. So there's been a lot of work on signal decomposition on over complete basis functions. And the application to video. One of them is by Ralph Neff and myself, which was published in '97, and since then we've published a lot more. But it's based on a technique called matching pursuits. But most recently, folks at Donahoe, who used to be at Berkeley, but unfortunately he moved to Stanford in the stat department, he has come up with a technique called basis pursuit, and I'm happy to say he came up with basis pursuits while at Berkeley, not at Stanford. And you can go to his webpage and look at some of the papers. Actually, you know what I noticed? The word before the space before the word Donahoe on that web address on the paper should have a tilde, and it doesn't. That's on page 4. So you might want to add a tilde there. So besides matching pursuit, best basis pursuit is yet another way of doing things. And then a third way of doing sparse signal approximations. Okay, why are these things important? Is because they enable us to represent signals in a most compressed, efficient way. And you'll learn more about these when we get to the compression part of the course. Unfortunately, there's a bit of a kind of a shift or a mismatch between what we cover now and what some of these things cover. So the third technique is called SBL, which is sparse Bayesian learning. And people like Tipping and Delgado and Rao have all, and the references for these are at the end of the paper, have all come up with ways of doing it. So if a group of you wants to do a project, and on top of all this, I have a grad student, Pierre Garrigue, who is working on SBL. And so SBL is kind of the newest and the most, in my opinion, the newest and the most exciting one of these techniques. Now, to get SBL to work, you need to do very, very large matrix inversions. And we've already gotten a bunch of clues as to what techniques for matrix inversions you should use. And we could even use the Millennium system and the CS cluster to do that, but you really don't have to do it. You can do it on regular Solaris systems, and it turns out it takes about for a 128 by 128 image, it's an iterative SBL is an iterative process, and it takes about 10 minutes. The size of the matrix that you have to invert is 10,000 by 10,000 for a 100 by 100 image. So as you can see, the size of the matrix grows square of this dimension of the image. But even for that size image, it's no more than 10 minutes to do an inversion on today's computers and fast processors. So if you decide to do a project, it'll be fantastic to kind of implement SBL for a large image on a computer and investigate its compaction or properties. this is something nobody really has done. I mean, if you look at Delgado's paper, they go as far as an 8x8 blocks in an image. So would be interesting to know if you go to larger, if you apply this technique to an entire image, either 200 by 200 or 100 by 100, using fast inversion algorithms, how much performance improvement in terms of compression you can get out of it. Or if you don't want to get your hands dirty programming, you can do a paper in this area. Read some of the stuff I've listed here, and kind of provide an expose as to what the pluses and minuses of these schemes are, and the usual 3 things I ask in any paper. The last topic is really very blue sky, open-ended. This is the one that I just cut and paste from my proposal. It has to do with the project that's been going on in my group in the last 3 or 4 years on 3D city modeling. And most recently, we've kind of gotten additional support from the government to continue that work. And the gist of the project is that we built a system, a ground-based system that collects laser data from the facades of the buildings. Then we hired airplanes and helicopters to do laser scanning of the top of the roofs. So from that, we built the 3-dimensional texture for the roofs, and then from the ground-based laser system, we built the 3-dimensional models for the facades of the building. And the key issue in this whole project is registration. How do you register and fuse these multiple modalities of data? There's texture, which is intensity, to be collected from ground and sky. Then there's geometry to be collected from sky and ground. And so how do you fuse these things? So we've come up with methods to do that, and I've listed the 4 or 5 papers by Frue and myself that addresses this. Where to go from here? Well, there's essentially section 5.4 and 5.5 are the possibilities. And again, what I put down here is very much image, object recognition, target recognition centric. For example, what I'm talking about here, okay, now that we have a 3, so there's, let me backtrack. This method that I just described, you can go to our webpage, download 100 megabytes worth of zip data, which is a 3D model of downtown Berkeley. And for those of you who are video game generation, you can plug it into your Cosmo player, which is a VRML viewer, and interact with that model the same way as you interact with your video games. Like you play Madden football or baseball, and there's all these 3D things you've got straightened out in your head. And by the way, your generation is supposedly a lot better in these 3D aspects than our generation, because you played so much more video games. I played video games too, but mine were strictly 2D. So my 3D sense is not as developed as even my 12-year-old son, but that's a different point. Anyway, you can download these 3D models. You can plug it into your Cosmo player, and there's a rotation button, and there's a zoom button, and there's a pan and tilt button. And you can fly over the model, like fly over Berkeley. You can come down, walk over Berkeley, or you can drive through Berkeley. Whichever way you control this, it's kind of like a flight simulator, if you will. And if you don't like to do any of these things, again, on my webpage, you can just download the video that shows all of these things and watch the video. In any event, so the models are there, and what section 5.4 and 5.5 talks about is, okay, now what are some interesting things we can do in those models? Well, if we sprinkle them with lots of surveillance cameras and network of cameras, you can do a lot of tasks that people have traditionally done in image processing with a single camera without a knowledge of the surrounding scene around them. You can do them much better by having a network of cameras sprinkled throughout this 3D world, whereby each camera also has inherent and intrinsic knowledge of the 3D model, where it's sitting with respect to the world, and carry out traditional tasks such as tracking an object, such as surveillance. Did anybody pass this part of the street in the last 24 hours? Who did? How fast were they moving? Where did they go? This camera can track it for this piece and then relay that information to the next camera and say, oh yeah, that's the same person I tracked, you not track it, etc. So there's a bunch of tasks that you can do. Can we sprinkle the cameras in such a way that we have complete knowledge of what's happening in a particular region without missing a car passing by or a pedestrian passing by? Even with the 3D modeling aspects, there's a lot of loose ends that interesting projects or paper can be done. Uh, if you model downtown Berkeley and don't simplify your models, you end up getting huge amounts of data. So applying simplification techniques that preserve the architectural details and keep the buildings as a box-like thing rather than a sphere type thing. If you apply traditional simplification, for example, to the geometry, you'll end up rounding the buildings and making it look like a ball, and all kinds of bad things happen. If you don't simplify it, the models are too detailed to be viewed with any realistic VRMO viewer like Cosmoplayer. So you're kind of stuck between a rock and a hard place. So coming up with simplification techniques that effectively simplify while keeping the building architectures as square and Manhattan-like as possible is kind of important. Indoor modeling of buildings, that could be a very interesting term project. What are some kind of a literature review of what people have done for indoor modeling as opposed to outdoor modeling? And again, I have ideas of how to do that. Once you have the 3D modeling, you've got sprinkled a bunch of cameras, you can then build models of the moving objects using these cameras, transmit this to some sort of a central station, and have those videos and models be inserted inside the pre-existing static 3D model that you've already constructed. So you can imagine that we've put a bunch of cameras and it's on Shattuck Avenue, right? And we already have a model of that Shattuck Avenue region, which we do, and people are in some CIA headquarters or some whatever are watching the 3D models, but then you can insert the dynamic objects or the moving objects from that region into the 3D model and have people view the traffic and the moving objects remotely in that model. So there's a whole lot of things you can do here, and I've listed some of them. If you, there's almost too much listed here. So if you find yourself not, it doesn't mean your paper has to address all of these things, right? You can pick just a small aspect of it, a piece of it, and investigate that. Okay. And at the end, there's references. It's kind of a mixed thing. I put some papers for some of the topics in the middle of the text, and some of them at the end. But it shouldn't really matter too much. So let me stop at this point and see if there's any questions. Questions, comments? Okay, how many people have already more or less decided what they want? I think we did the show of hand before. Have more or less decided what they want to do. Oh, wow, excellent. Okay, so those of you who are still thinking, feel free to contact me. Come to the office hours, and we'll get going on it. Any questions or comments at this point?
Yeah, should we, if we have ideas of topics that are should we talk about them before we write this proposal thing that's due in a week or whatever?
Oh, sure. I'd be happy to talk. You don't have to, but
Okay.
if you want us to converge faster, yeah. Yeah.
I'm going to be at a conference from the 5th to the 14th of May, so could I just go early if you plan on having presentations that week or something?
5th to 14th. We'll cross. Let me look in. So when was the thing? 15th of May was the.
Right, but for the presentations, could I just go like before I leave or something?
Oh, okay. Yeah, we can accommodate you. Okay. Any other questions or comments? Okay. So I'm going to go back and talk about the histogram equalization, which was a method for sharpening or method for enhancing images. So what we talked about, if you can possibly put the camera on the on the monitor. All right. Oh man. Yeah. Okay. So what you see in these pictures are this pollen SEM that with different levels of darkness and different things added to it, and it shows the histogram, corresponding histogram for this image. And as you can see, the most appealing one is the bottom one. It has the right level of sharpness and contrast. And if you look at the histogram, you can see it's more or less flat. So what we decided, what we concluded last time, it's a good what's a good thing to do is to, if you start with images whose histogram is not equalized like this one, which is shown here. If it is too dark or it's too bright or it's a low contrast image, which is a compacted histogram here, one way to quote-unquote fix that image or to enhance that image is to transform each of the pixels, uses a simple transformation technique or devise a transformation technique that will flatten the histogram, which is shown here. And so what I'm going to talk about now today is really a way of coming up with the pointwise transform. R is the intensity value of a pixel, and we're assuming it's normalized between 0 and 1. We're going to come up with this curve T of R, which maps R sub k, a particular kth intensity level, to S sub k. So that pixel gets transformed to that value, and thereby causes enhancement. So the question is, how can we design this T of R? And the answer is that we can do that by just looking at the intensity values of the pixel itself. So it's a signal adaptive transformation, if you will. We build this transformation by looking at the histogram of the image itself. And I'll come back to this picture in just a second. But if you apply this histogram I talked about it a little bit last time, but if you apply the histogram equalization to each of these dark or bright or low contrast images using the right transformation, then you end up with these images that are all enhanced and good. So there is light at the end of the tunnel, and as an example for these 4 images. And these are the 4 transformations as input versus output. This is R, and this is S. These are the 4 transformation, number 1, number 2, number 3, and number 4, that were applied to these 4 images that resulted at the end to get a histogram equalized one. So you want to come up with a technique that no matter what's wrong with your image, the final processed image looks good, right? So what is that methodology? I will talk about 2 things. One of them is called histogram equalization, whereby we apply a transformation where the resulting image has a uniform probability distribution histogram. And then the second method is called histogram matching, where you have a desired histogram. You want the output image to have a desired histogram or desired probability distribution function. And now what transformation do you apply in order for the final output to have that distribution? So those are the 2 things that I'm going to talk about. And in an informal way, in the last lecture, I already talked about both of those, how we do that, just kind of the mechanics of it. But in today's lecture, I'm just going to provide a little bit more mathematical analysis of that technique. So today's lecture is really on mathematical aspects or derivation, really, of histogram equalization. And and just so that, because last time's lecture was on Friday and it's been 5 days since you saw this, let me just briefly, before I get into the mathematics, let me just briefly describe to you or remind you what the intuitive understanding of this thing was. Here we go. So, excuse me. So, if you can zoom in, please, as much as you can. Thank you. Okay, so if you have, if this is the probability distribution of the input intensity, and it's kind of skewed this way, goes down this way, and so this is P sub f, the input image, and this is P sub d of g, the desired histogram at the output. And it kind of looks a little bit more centered and more equal, spanning the whole range. And in this case, we're just assuming we have 15 values of, or 16 values of intensity. And we're assuming that we're dealing with a 8 by 8 or 64 value point image. Okay. So the first thing we do is we build the CDF, cumulative distribution function, for this probability. And as you all know, CDF is just the integral of P of f. And we also build the CDF, which is the integral of this distribution. And these are shown here. So this is the CDF of the given input. And this is the CDF that we would like to achieve. And so, as I explained last time, if you can zoom out just a little bit, and I don't really know whether you can read the numbers or not. So the way it works is, so at the end I want to come up with a transformation. For example, I want to know input intensity 7 should get mapped to what output intensity. And the way I do that, the number on top of these bars, I know you can't read it, but essentially shows the height of each bar. For example, at 7, the height is 56. At 6, the height is 52. At 5, the height is 48. What that means is that 48 pixels have intensity of 6 and smaller on the input image. So this is what we mean by the CDF of the input image. By the time to get, because this image only has 16 intensity values, by the time you get to intensity input intensity 15, you've reached 1, which means in this case is 64. That means all 64 pixels have intensity 15 or lower, right? So this is the shape of the input CDF, and this is the shape of the CDF we desire. So let's see. We want to figure out, for example, what the input intensity value is 6. What does it correspond to? So you go up, look it up. Here it's 48. That's the height of this bar. And then you come down here and you look for 48, and you see, well, this is the bar that corresponds, that has height 48. And you come down and look it up, and intensity is 10. So input intensity 6 is matched to 10. And you keep repeating that for every input intensity in order to find out what output intensity it's matched. And this is kind of the transformation you get. And after you apply this transformation to this input distribution, this is the PDF of the input that you get, of the output that you get, which is quite a bit better than what we had before. It used to be like this. Now it's a little bit more centered. So what I want to talk about today is kind of the mathematical derivation of why we do what we do. Where did it come from? I mean, it's kind of, I told you what we do, but I never told you how come it works and why it works. Okay. So the setup is the following. For this derivation, I'm going to consider a continuous values of intensity. Okay. Rather than discretized, and I'll discretize this in just a second as well. Okay, and I call that R. Okay, so R is just the gray level of image to be equalized, and R has been normalized, we assume, to the range 0, 1. So 0 corresponds to dark, and 1 corresponds to bright. In other words, dark, i.e. black, bright, i.e. white. Okay. And now the goal is to design a transformation and we call that transformation, as you saw on the screen, T of R equals S, for the range R between 1 and 0, and also S between 1 and 0, that we're gonna that results in a particular probability distribution function that I'll just talk about in just a second. So we're assuming, to begin with, again, these are a set of assumptions. This is a transformation that does histogram matching or equalization. It does histogram matching or equalization. This is the thing that we're after, mathematically or numerically, if you will. We're after this transformation. And we're going to make the following assumptions about T of R. And the reasons kind of become clear in just a second. You can roll up just a little bit. So here are the assumptions. Assumption A is that T of R is single valued and monotonically increasing. And I'll explain the reason for these assumptions in just a second in the interval R between 1 and 0. Okay, and so before I even do that, I'd like to go back to this picture. If you can switch to the computer for a second. So what do I mean by it's single valued? That means that for every value of R, there's a single there's a single output or single corresponding T of R. Okay, so the curve, for example, can't come up here, go back up, and then come back down this way. There's not two values associated to. There's not two T of R's associated with a particular value of R. Let's put it that way. So the single valued, why do we want this to be single valued? Because we want the inverse transformation to exist. So this is needed. Single valuedness is needed for the inverse transformation to exist. So here's R. Let me just draw it here. Might as well do that. So we don't want this thing to do this. Here, this is not single valued. For this value of R naught, we've got two values of S. Okay. We also want this to be monotonically increasing. So why do we want this to be monotonically increasing? Well, in that interval, because otherwise, what happens? So this is not single valued, and this is not monotonically increasing. If you can go down a little bit. So okay. So what happens is, why don't we want T of R, the transformation that takes input intensity to map it to the output intensity, to kind of do that? Because there's some intuitive thing that we want to preserve the increasing order of black and white in the output image, the same as input. Because, for example, what happens is that if the input image R naught gets mapped to S naught, intuitively you would like higher values of R naught to get mapped into higher values of S naught. Otherwise, there's a reversal of brightness going on in the output. That, I mean, artistically it could result in a fun image. You could sell it and make a lot of money or something. But from an intuitive point of view, you want the same way as the input intensity values progressively increases from left to right. You want the output intensity also to follow that curve. But how that curve is whether it's going to do this or this or this, whatever. That's what we're after. We want it to be monotonically increasing. We don't want it to go up and down, etc. So the reason for that is because we want to preserve the increasing order from black to white in the output image. Okay. And so this is condition A. So we're assuming that our transformation satisfies these conditions. And then condition B is that we want T of R between 1 and 0 for R between 1 and 0. And why do we want that to be true? Well, because we want the if the input intensity R ranges between 0 and 1, we want the output intensity S, which is T of R, to also vary between 0 and 1, because we want the output to be in the same range of intensity values as the input levels. So intuitively, the reason for this is we want the output gray levels in the same range as the input levels. Okay. So clearly, if you switch back to the computer for just a second, yeah, sure.
Yeah, I'm just a little curious from last lecture about what this transform is actually doing. So, I mean, is it going to take some intensity R in your original image and then multiply it by this value of S or something?
Not multiply, map it. It's a table lookup. It's a table lookup.
Okay.
So, for example, this is the best way of kind of intuitively explaining it. Here, when the transformation is all said and done, okay, so this is the final transformation. You store that as a table lookup. You say all the pixels that have input intensity 1 are going to map to output intensity 3. All the pixels that have input intensity 2 are going to get mapped to 5. So you store this table and you just get the input image, look up the intensity of each pixel, and then look it up in this table and figure out what the output intensity is. Is that clear?
Great, yeah.
That's exactly what we're doing. And by doing that, now the histogram is much better shaped. Okay, so coming back to here, go back to the computer. So this particular transformation satisfies all of these things. It's monotonically increasing, it's single valued, and it ranges between 0 and 1, just like we wanted it to be. Okay. So having set up all of these things, what can we say about histogram equalization? Okay. So T of R is S, and furthermore, T inverse of S is R. And remember, R is the input intensity input intensities, and S is the output intensities for a given pixel, or for each pixel. Okay. So there's a major result from probability theory that says the following. So result from probability theory that says that if T inverse of S satisfies condition A, that I just listed, then the probability distribution of S and R are related in the following way. PDF of S is related to PDF of R through this relationship. Okay. So that's straight from probability. And then rolling up the camera one more time. And so based on this, we can now figure out why we build the CDF. So consider the CDF thing that we've been talking about as a transformation for a long time. So if S is T of R, CDF is in the continuous domain is essentially the integral of the PDF, PR of omega, PR of W, dW, ranging from 0 to R. Okay? So this is the CDF of the probability distribution of the input pixels. And now we can apply straightforward calculus, ds dr. What is the derivative of this transformation? And by definition, what is it? What is the derivative of this with respect to r? Because the integral here is all the way to r, it's nothing but p sub r of r. Okay? So if we have a transformation which is CDF, which is the one I just showed you an example of, we just all along, then this derivative is p sub r, and now if I plug this into this relationship, what do I get? I get p sub s of s is p r of r times 1 over p sub r of r, which is just 1 for s in between 1 and 0. So what does it say? It says if we apply this transformation, the output is going to have probability distribution function that's uniform. So in words, what we have is if the T of R is just a CDF or just the integral of input PDF, which is P sub R of R, then applying T of R results in an image whose PDF is uniform, which we call P sub S of S, is uniform. And this is exactly what we mean by equalization, histogram equalization. Histogram, you can think of it as the same as PDF. When we say it's been equalized, that means it's become a uniform, equal for all heights. Uniform, it's become a uniform PDF. Okay, so that's kind of an interesting, exciting result. That's why we use, that's why we start with PDF and we kind of go to the CDF domain. Are there any questions? Now the next thing I wanted, so this is all good for continuous, and in case you're terribly worried that it doesn't work because pixels have discretized amplitude, let's just briefly extend that to the discrete case so your mind is at peace. So so now consider the discrete case. Okay, so now we have R sub k, which is the discrete intensity values for k ranging from 0 all the way to L minus 1. And in that case, probability of R sub k, probability that we get intensity value R sub k is n sub k over n, where n sub k is just number of pixels that have intensity in the image that have intensity or level R sub k. See, the beauty of images, I mean, deep down what's going on, the beauty of images is that it's got so many pixels. Like if you got a 100 by 100 image, you've got 10,000 pixels. And you can easily build PDFs from the image itself. And that's why you can kind of mix histograms and PDFs in a nice way. When you're dealing with communication system design, for example, and you're talking about statistical ergodicity theory or something, you don't get so many instances of the statistic that you're dealing with, and therefore a lot of the statistical averaging things there are much harder to deal with than when you're dealing with images. Anyway, so in the case that R sub k is some discrete intensity values and n sub k is the number of pixels that have intensity R sub k, then and n is off, and here k ranges from 0 all the way to L minus 1, and what we have now, S sub k, is the transformation of R sub k, which instead of being the integral of the PDF for R, it's the summation from j equals 0 to k of p sub R taking on the value R sub j. This is the transformation that results in a uniform histogram, or in an equalized histogram, which we can also write down p sub R as summation from j equals 0 to k of n sub j over n. Again, all k ranging from 0 to L minus 1. And so what the transformation now that we have, r sub k, s sub k, is going to look something like this again, or some variation of this. You look up a given intensity value, you look up in this transformation to see what the output intensity value should be between 0 and L minus 1, 0 and L minus 1, and boom, now you have a table lookup method of doing this. Okay? So does anybody have any questions regarding the discrete case? It's very much analogous to the continuous case. The integral has just been replaced with a sum. And the last thing I want to talk about is histogram matching. So far, we've been dealing with this problem whereby we have an input image. It has a PDF. We have a PDF for its pixels, and we want to transform it so that the output image has a uniform PDF distribution. What if you don't like uniform? And I'll show you an example of this in just a second. What if you really rather have a different histogram for practical reasons, for reasons that come from the application domain? How do you do it then? How do you design the transformation then? And actually, the answer is not that hard. So let me just derive that also. So this is called histogram, not equalization, but matching. Okay, so T of R is S, and rather than making P of S uniform, we are given, we want the P of S to match a desired, if you will, PDF, a desired given PDF. It's kind of like an inverse problem. Here's a PDF of the output. Go design the transformation so that the output will have that kind of a PDF. So here's how we solve it. We say R again. Well, again, I'm going to do it in the continuous domain because transferring it to the discrete domain is trivial. It's just a matter of replacing integrals with sums. So R is the pixel values before equalization. And Z is the pixel values. Actually, let's not call it equalization. Before matching, because now, strictly speaking, we're not doing equalization, we're doing matching. We're modifying histogram, but not to equalize it, but to match it to some other thing. And this is pixel values after matching. Okay, so then we're given, we can compute from the given image, we can compute P sub R of R from the given image. Okay, and we can we know, or we're given P sub Z of Z. This is somebody has come to you for some reason. You believe the output distribution should look like P sub Z. That's the one you got to match. So how do the question is, what is the transformation? So the goal is what is the transformation from R to Z? How do I design that? Okay. So once again, and this might sound a little bit surprising to you. Once again, I'm going to build the CDF for R, and I'm going to build the CDF for Z, and then do the matching in the CDF domain. And let me expand on that a little bit more details. So the approach that I'm going to take is I'm going to build S as T of R, which is integral from 0 to R of P sub R of W dW. This is the CDF, cumulative distribution function of R. And I'm going to build a new transformation, G of Z, which is the CDF of Z. It's 0 to Z, P sub Z of T dt. Okay, and this is the CDF of Z. And our goal, remember, is to make um, because we want P of R, because we want the output to have distribution of Z, uh, essentially the histogram matching histogram matching corresponds to G of Z to be equal to T of R. That's really the transformation. We have to design T in such a way that after we apply T to R, we get this guy G of Z. And so, in other words, we want Z to be the inverse value of T of R. So what does it mean mathematically? Well, or algorithmically? Here's R, and what we're gonna so here's R, and here's S. Oh, and it's going to be so now I'm going to plot the CDF of R 0 1 0 1. So this is just the CDF of my intensity values R, and then I'm also going to build a CDF for Z, and I call this V. So this is Z 0 1 0 1. I call just G of Z V, just for the sake of completeness. So I'm given this kind of CDF. That's what my image has. And this is the kind of CDF I want to have. This is where I am. This is where I want to go. So what should be the transformation between R and Z to make this happen? When I have an intensity value R, what do I transform it? What value of Z do I transform it to such that the resulting image will have this kind of desired CDF? Well, the answer is pretty straightforward. Let's say I want to know what the mapping for R naught is. I pick a random value R naught, and I want to know what value, how to find Z naught, the map for R naught. And how do I do that? Well, the easiest thing to do is to go to this curve, go all the way up until you hit the curve, and then look up this value, whatever T of R is, T of R naught is. And because I want T of R naught to be the same as G of Z naught, I go to this axis now, and I look up where T of R naught is, and then I go all the way here until I hit this, and I find the corresponding Z naught. Okay? So this is the procedurally, this is the step we take, which is not that different from the one I talked about earlier at the beginning of the class. And there's just more mathematics kind of associated with it. Okay? And I keep doing that for every R sub I. Then I do that for R sub 1. So now having done that, remember I'm building a table now. So my lookup table will have, R naught gets mapped to Z naught. How about a new value like R1? Well, here's R1. This is T of R1, and then I come here and I find T of R1, and that gets maps to Z1. This is how I find it. Okay? And I keep doing that for every intensity value until I have this table lookup, and I end up getting this is called this. Now I have matched the histogram of P sub Z of Z, which was the desired. Okay. So let me show you an example. Is this thing mostly clear? Okay, so let me now show you a real-life example where we don't want to just equalize the histogram. We want to do a little bit more. So if you can go back to the computer, please. Okay, so here's the image of Mars, moon, that NASA got using the global surveyor. And this is the histogram of that picture. Okay. And you can see that, you know, this region basically is way too dark, and this region is too light. Now, if you just do the good old histogram equalization, in other words, make the PDF of the output be uniform, we get this picture, which is already better than what we started off with. We had this as input, this as output. Okay. So, and how did we get this picture? Well, this is the input gray level, this is the output gray level, this is the transformation we applied using the histogram equalization method. So that's the transformation. And at the end, when all is said and done, the histogram of the output looks something like this. So there's no intensity values between 0 and, I don't know, 150 or so. And you might say, gee, there must be something wrong. If you really equalize histograms, this is going to be uniform. But it's not, because these mappings that we deal with are not necessarily onto and one-to-one and various other things. And so this is the best that histogram equalization can do. So you look at this image and you say, you know, I really don't like the fact that this is too bright. And as such, I'm going to come up with a desired histogram that's kind of more dark. And this is kind of the histogram that you come up with. You shift things to it's more or less equal here, but then you shift things. You want to have a big, this is the desired PDF of the output that you come up with. And now this shows the G function, G of Z, and this shows the G inverse. And now if you apply the histogram matching, where you're matching this kind of a PDF, you get this kind of the histogram as the output and this kind of an image, which looks a lot better than if you simply did histogram equalization. So as you can see, the histogram before, this is before, the histogram was shifted here. It was from 150 onwards, and now it's shifted a little bit to the left to 64. And if you're still not happy with that, you can move things to the left even more. Question?
So the thing we're tweaking is G of Z, right? To make that's what we're trying to match.
No, strictly speaking, yeah. You come up with the P of Z. You come up with this is the same as G of Z, which is the integral of it. That's right. So you might, so yeah, you've changed one tweaking to another tweaking, right? Depending on how you pick G of Z, you could get different images, right? And in this case, intuitively, we just looked at this, and we saw this is too bright, and we said, okay, now we're going to make our G of Z, which is the desired probability distribution function, move to the left a little bit. This is the desired that we came up with, and that desired results in this G and this G inverse, the transformation, and the final histogram looks like this. I think I'm going to stop now. I will continue this discussion on Friday. And one announcement I forgot to say, don't forget to hand in your lab assignment on Friday.